Hi, my name is Kristina Kwan, and this is my group's build for the Tekrocks Bridge Challenge. As the mechanical engineer on the team, I, along with my teammates, designed a rotating bridge that allows for boats to sail up and down the river and cars to drive over it. I created detailed pre-build and post-build diagrams with correct labels, as well as an accurate parts list of all of the VEX parts that we used to create the bridge. Additionally, while completing the physical build, I made sure that the bridge was aesthetically pleasing and that it functioned properly. Firstly, in terms of mechanical systems, we incorporated a 2-gear system with a 12-tooth input gear and an 80-tooth output gear, which was built into a mechanism called a turret. The input and output movement of the system are both rotary, and in using a smaller input gear, we decrease the output speed and increase the output force produced by the system, allowing the bridge to rotate more slowly and therefore more safely. If we had used a smaller input gear, the output force would have increased even more, and in contrast, if we used a larger input gear, the output force would have decreased, but the output speed would increase. Output speed and force can be tested by observing the movement of the output gear in relation to the input gear. For example, if the output gear spins once and the input gear spins twice, the output speed has decreased while the output force has increased. In contrast, if the output gear spins twice while the input gear only spins once, the output speed has increased while the output force has decreased. As for testing the direction of travel and flow of power, there are a couple of tests. To test the direction of travel in a mechanical system, you would move the input in the opposite direction of normal travel to see if the output still functions. And to test the flow of power in a mechanical system, you would move the output to see if the input moves. Another mechanical system we could have implemented into our bridge was the worm wheel. Because both the input and output movements are rotary, the output force is increased and the output speed is decreased. The direction of travel is reversible, which is compatible with our bridge, and although the flow of power is not reversible, that would not have affected our bridge either. As for specific building techniques, we utilized quite a few. First, we use specific screws to mount motors. VEX motor screws are thinner and smaller than regular VEX screws. And in terms of determining which type of regular screw to use, I always choose the shortest screw possible. Screws should typically face inward so that they don't interfere with the build's movement. However, a lot of the screws in our build face outward because facing inward would have interfered with the car's movement across the bridge. Moreover, shaft collars should always face the same direction for greater efficiency when tightening or loosening. 2 VEX parts that must be used to avoid metal grinding on metal are the shaft bearing and the spacer. Specifically in our build, we used a few spacers, but we did not use shaft bearings because we only had one shaft and it did not go through metal. I experienced a multitude of challenges while completing this build with my team. Most notably, we had immense trouble mounting the turret onto the base plate while allowing for enough space between the two for a motor. Originally, we had planned to use standoffs to elevate the turret. However, we later realized that the standoffs would not provide enough stability. And so after a lot of trial and error, we ended up using 2 bevel gearbox brackets to allow for maximum stability. In doing so, we were left with a simple mechanical system that functioned properly and was aesthetically pleasing. As for what I was most proud of accomplishing during this build, I'm most proud of the way we chose to link the bridge and the platforms. Originally, there were gaps between the two because without it, the bridge wouldn't be able to rotate properly without crashing into the platforms. While figuring out how to bridge the gap, I learned to cut bars and file them, and I also learned about another VEX part, steel washers. After using 5x6 plates and bars of various lengths to bridge the gap, I used 16 steel washers to elevate the C-channels that made up the lanes of traffic, and as a result of our efforts, all the parts of the bridge lined up, functioned properly, and looked aesthetically pleasing.